Thanks very much. It's a pleasure to be here. Thanks for the invitation. So just so we're all on the same page, I'm going to start just briefly mentioning how Grothendieck and triav invariants work, although I bet most people here are familiar with this. So representation theory gives invariants of links. And let me just give it a quick example. So here's sort of a nice link. And you might take this link and label it with a representation V. So V is going to be some representation of a Lie algebra G. And then to each piece of this, you sort of associate a morphism between tensor powers of V and V dual. So for example, this might be associated with the identity of V tensor V. And this right here might be a map from the identity, which is sort of the cross-section there, to V tensor V dual, which is the cross-section here. So I'm reading this now from bottom to top as a map from the nothingness, which is the monoidal identity and representations of V, to V tensor V dual, to V tensor V tensor V dual, and so forth. And I keep reading to the top. And in the end, I get a map from the trivial representation to the trivial representation. Is this already a familiar story to people? So what are the building blocks of this thing? I mean, you need to know what happens to your cups and caps. So this is some map from V tensor V dual to the identity. And you need to know what happens to your crossings. This is some map from V tensor V to V tensor V. And then when you're done, you compose to get an element of endomorphisms of the monoidal identity, which in this case is the complex numbers, and so you get a number. And for example, if you say take the Grothendieck and Turayev, this is called the Grothendieck and Turayev invariant. If you take the Grothendieck and Turayev invariant of the unknot decorated with V, you just get the dimension of V when appropriately interpreted in this category. Dimensions can be negative. It depends how you think about things. I'm about to. Oh God, how do I do this? I'm about to. So these invariants are boring. They only become interesting when you quantize, okay? And so now you can let V be a representation of the quantum group. And that makes the crossing map more interesting. And so for example, when you quantize the endomorphism of the monoidal identity is QQ, but whereas in fact all the invariants live inside as EQQ inverse. Cups and caps are just built into the fact that you're in a pivotal category. Rep G is a pivotal category, is rigid monoidal. Yes, this is all built into the structure of the quantum group algebra itself. This is all standard, yeah. Standard structure in Rep G, in Rep QUQG. These are structure. But I mean, every V comes with this.
But does it come with it by virtue of being dualizable, which is a property, or is it a data that you use?
I'm not 100% sure. I'm pretty sure for finite dimensional representations, it's a property because I think it comes for free. Okay, so so in this case, I just want to give you some examples of what you get. So in type A, when say G is SLN, so if V is the kth fundamental representation, so if you were doing this unquantized, this representation is the kth wedge product of Cn. Okay, and so its dimension is n choose k. And if you're doing this quantized, so if you take this kth representation and you do this and you do the quantum version, which I'm just going to do right in the queue, then you get the n choose k quantum number, so the quantum binomial coefficient. Meanwhile, if you're doing this, say, for example, in type B, so let G be SON plus 1, 2n plus 1, and let V be the last fundamental representation. So unquantized, this would be the spin representation, also known as S. Okay, so the dimension of the spin representation is 2 to the n. Okay, and when you actually take the Grothendieck derivative invariant, you take the quantum dimension, if you will. I'll just write S. You get quantum 2 sub q, quantum 2 sub q cubed, quantum 2 sub q to the 5th, all the way up to quantum 2 sub q to the 2n minus 1. You get a power, like a quantum 2 power, if you will. And so this is like, in case you don't know, this is q plus q inverse, that's q cubed plus q to the minus 3, and so forth. Okay. Great. Now, the Grothendieck triad invariants have a categorification. So what does that mean? Yes, I have to do this right in the middle. So there's a categorification due to Khovanov-Rozansky. So the Grothendieck invariants of SLN have categorification, the Khovanov-Rozansky categorification. Okay, and what this is some sort of graded vector space, KR of your sort of link with parameter labeled with a vector space for the representation. And it satisfies the property that if you take the graded dimension of the Khovanov-Rozansky homology of your link, and then you get the Grothendieck triad. Okay, where Q represents a graded shift. So technically, this Khovanov-Rozansky homology really should take a complex of graded vector spaces and take its Euler characteristic. But I'm not going to go into so much detail just yet. I want to talk about the motivational examples here. So if you were trying to come up with a vector space whose graded dimension was quantum n choose k, there's a very nice, easy, classical example. So the Khovanov-Rozansky homology of a sort of circle labeled by a k fundamental representation in type A is precisely the cohomology of the Grassmannian of k-planes in n space. And this cohomology has a sort of nice basis in bijection with partitions in a k by n minus k rectangle. So in this case, if we're going to do k equals 2 and n equals 4, then the partitions fitting inside a 2 by 2 rectangle look like this. And so if you count these things and you appropriately shift their dimensions, this gives you a factor of q to the minus 4, q to the minus 2. We got 2 q to the zeros, q squared, and then q to the 4th. So when I add all these things together, I get quantum 4 choose 2. Okay. Any questions about this? You can use that as your definition of your quantum binomials if you like. Now, what do you get when you look at the Grothendieck triad invariant of SO5? So this example on the right-hand side of a circle labeled with a spin representation. Well, you're supposed to get quantum 2 sub q times quantum 2 sub q cubed, which is q to the minus 4 plus q to the minus 2 plus 0 q to 0 plus q squared plus q to the 4th. Okay. Is this the graded dimension of some vector space? Or perhaps better, is this the graded dimension of a nice, like, projective algebraic variety? Anyone want to tell me yes or no? Yeah, then definitely not. The reason this cannot be is that like nice, smooth projective varieties have a hard Lefschetz theory, which basically says that you've got the graded dimension of an SL2 representation. It's balanced around the middle, but you've got some sort of raising operator, which is an isomorphism from bottom to top. But I can't go through 0 and be an isomorphism. Okay? Cohomologies of nice varieties don't have holes in the middle. Okay? So you should not expect this to be categorified in a similar way to Khovanov-Rozansky, where you end up with a nice cohomology of a space. Okay? However, I've actually already given you the categorification of this, and it's already on the board. Okay? Because, so the point is that this is not H star of something nice. Okay? So you should not expect traditional categorification to work. But there is an action of Z mod 2Z on this space. Okay? And I'm going to call the generator of this, I'm going to call this generating involution tau. Okay? And what tau does on this basis is that tau is the transpose of a partition. Okay? So tau fixes this, tau fixes this. Tau will swap these two. And then tau fixes this, and tau fixes this. Okay? So the graded dimension of a vector space is the trace of the identity, basically. Okay? But the quantum trace of the identity, if you want to call it. But if instead I take the trace of tau, okay, then these two things basically cancel out, and I'm just left with this. Okay, it's a 2x2 matrix. Okay, you'll see why they cancel out in a second. If you want, if I had chosen a different basis, then it would look like this, and that's why I say they cancel out. Okay. Any questions? So this is going to be our motivational principle for how we're going to categorify type B spin-colored Grothendieck invariants. What we're going to do is try to put some sort of involution on type A invariants, and then take the trace. So let me just state a theorem. Although how this theorem is proven is kind of surprising. Yeah. Yeah, so the point is that the vector space is the same vector space. But instead of taking dimension, you take the trace of an involution. So here's a theorem. Yeah, you're not going to get a vector space. You're going to get a polynomial in Q. The theorem is that there exists an involution, tau, acting on the Khovanov-Rozansky SLN, SL2n, sorry, homology of a link where every component is labeled by sort of the middle exterior algebra, or the middle fundamental weight. Maybe I was writing this before. So for any link such that the plus or minus 1 eigenspaces of this involution are link invariants. And then the theorem / conjecture is that the trace of tau on Khovanov-Rozansky homology is the Grothendieck invariant of the spin-colored link, the same spin color.
In your opinion, is that the categorification of spin thing is not a categorification in the same sense?
It's not a categorification in the same sense. And I'll explain to you in what sense it really is a categorification, but you'll have to wait for that. Right now, I'll just say it's the trace of an involution. And it's a theorem for small n, and the conjecture in general, but the conjecture has been reduced to some sort of purely algebraic nonsense that really has nothing to do with categorification. Just some statement about representations of SON that is not in the literature.
And the odd eigenspace, does it have,
Right, so the plus one eigenspace is like quantum 5, and the minus one eigenspace is like 1. So this is 5, this is quantum 5 minus quantum 1, right? Right, so the plus one eigenspace and the minus one eigenspace are two positive numbers, and I take their difference when I take the trace. Okay. Now, here's sort of a general remark. So people often associate type B and type A with folding. Okay? So the trace of on this 6-dimensional space here, the 1 plus 1 eigenspace is 5-dimensional, and the minus 1 eigenspace is 1-dimensional here in degree 0. And so the trace of tau is the dimension of the plus 1 eigenspace minus the dimension of the minus 1 eigenspace. So the graded dimension is the sum of these two eigenspaces. Sorry. 5 plus 1, sorry, thank you, is that, and 5 minus 1 is that.
The thing with Ben never produces a 4-dimensional vector space, which would be called categorification. Is that correct?
Correct. Are you happy? You seem unhappy still.
I'm not happy about it. Oh, it's different with the.
So, yes, I'm aware. This is totally different. Yeah, I know. I'm not going to give you a 4-dimensional. This is completely different. Please don't expect one. Yeah, this is unrelated to any other type B link invariance.
It's just a not,
Okay. So folding. So here's your type A Dynkin diagram. This is SL6. Okay. And this diagram has an involution, which I'm going to call sigma to distinguish it from tau because it's not tau. Okay. And if you take the orbits under sigma, then you get the type B, B3 Dynkin diagram. Here's A5. And, by the way, here's sort of, so this is SL6. Here's your sort of wedge 3. And this thing corresponds to the spin representation. Okay? So there is a long history of folding in the literature. And people have tried to folded type A, like quantum groups to get type B quantum groups. Like if you look at Lustig's paper, Lustig's original quantum group stuff, this is what he does. This is not what we use to produce tau. This is not what we do. That is to say, we're not going to take some type A thing and use this Dynkin diagram monomorphism and take some sort of folded world to get type B. We are going to be folding in a different sense. So let me explain that.
What was Lustig's motivation to consider folding?
Lustig's motivation to consider folding was this is the only way to categorify type B quantum groups, basically.
No, Lustig was not. Oh, I see. Makes sense. Okay.
Yeah. And he also does the trace of an involution on some stock of a perverse sheaf, yada, yada, yada. So it's a very similar construction what he does, but he does it for Dynkin diagram monomorphisms. So to explain what kind of folding we do, I have to talk a little bit about skew-Howe duality. What is skew-Howe duality?
Did he produce the polynomial?
No. So for any n, and I'm going to introduce a new number, d, what we're going to do is we're going to look inside representations of SLN. Everything's quantized. I'm going to ignore that quantum parameter when I'm writing things down. So if you take, say, the K1 fold exterior product of the standard representation, consider the K2 all the way up to the KD fold tensor product. And there's going to be d of these tensor factors. And I will get home from that to another d-fold tensor power. And I'm interested in HOMs from this default tensor power to that default tensor power as representations of SLN. The statement is that there is actually an action of GLD on this space. So if I take the universal enveloping algebra of GLD, let me quantize that, then this is going to act where, and it, like you should think that it's acting on the direct sum over all possible choices of K and L on all of these Hom spaces. Okay? And that the choice of K and the choice of L is actually a weight space for GLD. Okay? So I'm going to idempotensize it by putting projection to the K weight space here and projection to the L weight space there. So these K's, K underline, which is K1, K2, is a K tuple of integers, and you think about this as being in the weight lattice of GLD. Okay? And so the statement is that the part of GLD that takes the weight space K to the weight space L, which could be empty if K and L aren't comparable by roots, but is often non-empty if they are comparable. It is non-empty if they're comparable by roots. The part of GLD that takes this weight space to that weight space will also send this representation to this representation. Okay. Can I give you an example? Okay. Let me call this map psi. Okay. How many people here know webs? Okay, some people. Okay. So suppose that, like, over here, for example, maybe I've got, suppose that D is 2, just for fun. Okay? Well, we know that, like, the positive root of GL2 is like 1 minus 1, right? And so, like, the raising operator, E, would send something in weight 5, 8 to something in weight 6, 7. Okay, it would add 1 to this coordinate, subtract 1 from that coordinate. Okay? I claim to that raising operator, I should be able to associate a map from wedge 5, tensor wedge 8, to wedge 6, tensor wedge 7. Okay? And so I wanted to take this E to some map here. Now, if you know webs, there's a really easy way to write down a map from 5, 8 to 6, 7, and it looks like this. If you don't know webs, then what's really going on here in the middle of this web is wedge 5, tensor wedge 1, tensor wedge 7. There's some sort of co-wedge product from wedge 8 to wedge 1, tensor wedge 7, and then some sort of wedge product from wedge 5, tensor wedge 1 to wedge 6, and I do co-wedge wedge, and that's what this web is encoding. Okay? And so then the statement is that I can send E to something that looks like this. Okay? Now suppose that this was part of a larger thing. So suppose that D was bigger than 2, and I was looking at the weight space like 1, 2, 3, I don't care, 1, 1, 1, I don't know, 1, 1, 3, 1, 5, 8, 26, you know, dot, 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 going to 1, 1, 3, 1, 6, 7, 26, dot, 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 via, again, E. In this case, it would be the 1, 2, 3, 4, 5th raising operator, E5, in GLD. Okay? That would correspond to the web that looks like this. 5, 8, 1, 6, 7, 1, 1, 3, 1, 26, where you basically just take this thing that is easy to do and tensor with the identity map everywhere else. Okay? So there's D of these uprights. So there's D minus 1 places that I can put rungs, and there's D minus 1 raising operators in GLD. And so this is how you define the map on raising operators. The map on lowering operators is kind of the opposite. I'll just put it right here so we can get it all on one screen. So Fi is going to go to, in the ith and ith plus fish spot, a rung tilted the other way, the 1 on it. So that's going to go from A, B, to A minus 1, B plus 1. And so it's going to lower the weight. It's going to add minus 1 to this coordinate, plus 1 to that coordinate. Yes?
What's the action of Q?
What's the action of, like, the H, maybe?
No, because you've written sujection from the quantum, not just
Yeah, Q is just a parameter, and this is really like Hom as representation. All of these are vector spaces over Q. Q is just in the base field.
So the capital N basically plays no role in this?
Yeah, right. So the capital N plays a major role in that the n plus first wedge product of n-dimensional space is 0. Okay? And so any diagram that I draw that factors through a number bigger than n is 0. So this makes perfect sense when n is 5, except that every diagram that I just drew is 0. Okay? So there's some big kernel here, and the big kernel of this map depends on capital N.
And if this assertion is that it's not the assertion, every morphism of the
Yes, correct. So that's what skew Howe duality says. That's right.
who is dual to what?
What's going on is that really this big, giant direct sum of all tensor products is a huge representation on which there's a duality between the quantum group and like between GLD and SLN, kind of like in the sense of Sherwal duality, double centralizer idea. I want to point out that you can also describe the crossings in this language. So for example, if I was going to describe, oh yeah, maybe I should also say a little bit about divided powers. So there's this E divided K, which would map instead of to a rung with label 1, a rung with label K. E divided K, if you don't know, is e to the K over K factorial. And similarly, after the K is a rung tilted the other way. And then you can also define what a crossing is. Just for simplicity, I'll tell you the formula when these both have the same label. So this is like the 0 weight space for GL2, for SL2. And so the formula is that this is an alternating sum times Q to the something, which I neglected to write down so I don't remember, times E to the J divided J, F to the divided J, 1 times the weight space. I didn't put down a name for the weight space. Okay. So there's a nice formula for the crossings. Okay. So as a consequence of all this, the Reshetikhin-Turayev invariance of links, so if L is a link is a closure of a braid on D strands, okay, then the morphism from bottom to top that you're taking in this braid on D strands is an element that I can describe in terms of the image of this map. Okay, and then I close it up, and that's taking some kind of trace. And as a consequence, I can actually compute all of that. So this link invariant, then the Reshetikhin-Turayev invariant of L, is computable in UQGLD. Instead of thinking about representations of SLN, you can think about representations of GLD. Okay? And that is a very sort of different world, right? It's working on the other side of skew duality is working with a completely different Lie algebra. Any questions about that? All right. And I'll just mention, because it was asked, like, so phi has a kernel. And usually we denote, say, UQ less than or equal to n of GLD is the quotient by the kernel. And this has a name. This is called the Schur algebra. So some sort of finite dimensional algebra in each weight space. Okay. So one way, just like the decategorified statement is computable here, the categorical statement, the Khovanov-Rozansky homology, is computable in the categorification of the quantum group of type A. Not quite, yeah, singular Zirkel bimodules, similar. So, so this is a long story, okay, with many sort of players, like Khovanov-Rozansky, who defined, well, okay, maybe I'll get there. One way to categorify Khovanov-Rozansky is basically to categorify this thing and categorify psi. And this was done by a host of authors. So let me just quickly say what categorifies this. Many of you, I don't know, seem to work in this field, but many of you are grad students. You probably don't yet know. So there's this Khovanov-Rozansky 2 category. It's got sort of objects associated to weights, lambda. And so we think of these objects as being like, we often denote them as like one lambda, just like I've denoted weight spaces by one, these idempotency by one lambda.
This side or on this side?
I'm on the GLD side. I'm always on the GLD side when I'm categorifying.
Also on this side? Or?
Why don't you wait? Okay. It's got one morphisms, which are things like EI from one lambda to one lambda plus alpha I, and of course FI. And you also have these objects associated to divided powers. Okay. And then you've got some sort of two morphisms. And the description of the two morphisms was, where these things called Nilak algebras or KLR algebras or various things show up. This is complicated, and the main version I'm going to be talking about is from Khovanov, Lauda, Mackay, Stozich, which also has these divided powers inside it. But there's some graphical diagrammatic calculus that describes this categorification, and I sure am not going into that today. We don't have time for that, unfortunately. In KLMS, they are new objects. You should think of them as images of item. So this is a summand of EI to the kth power, And so you have to take a Kruby completion to get these things. Okay. And inside this categorification, we can categorify these crossings using complexes. So what?
What is the difference between GL and SL?
The objects. So for example, this complex here, before with A labeling both things, let me call this weight lambda, okay? Before it was categorified by this alternating sum. Where did I put that? Right here, this alternating sum. So when J is 0, this all disappears and I just get the identity, okay? And in homological degree 0, this complex is just going to be the identity of lambda. And then when J is 1, I get EF times the identity with some shift. And with a sign, which indicates odd homological degree. So the next thing I have EF, 1 lambda, and then E squared, E divided 2, F divided 2, 1 lambda, and then E divided 3, F divided 3, 1 lambda. And really, this goes on forever. But when it acts on any given when it acts on any given Schur quotient, eventually this thing is 0. Okay? So this is secretly a bounded complex. This thing is often called a Ricard complex or a Rugier complex or a Khovanov-Rozansky complex. I mean, like, a lot of people have contributed to this idea. Okay.
What was the first name?
Ricard? Rickard? Jeremy Rickard? Okay. So then to some sort of braid, like, I don't know, just doing some stuff, where these are labeled by sort of indices like K1, lambda 1, lambda 2, lambda 3. What I have here is some bounded complex well, if this is lambda on the bottom, I've got some sort of lambda prime, which is a reordering of lambda on the top. And it's going to be some bounded complex, which goes from lambda to lambda prime in this sort of Khovanov-Lauda categorification of GLD. This is supposed to be some sort of curly U, which is the categorification. Okay. All right. Well, how do you take the closure? What corresponds to taking this trace?
Are you doing the
So what?
Are you doing Webster's thing when you consider representation or something else?
No, there's no Webster here.
When you say bounded complex, before the thing was bounded.
It's only bounded in the Schur quotient. Yeah, that's why I put bounded in parentheses.
And the Schur quotient also makes sense in this categorified form.
Yeah, so the Schur quotient, that was done by Mackay Stosich Voss. So when the bottom and the top are equal to each other, then we can close the link up, okay? So we got this sort of braid, lambda prime. Sorry about not drawing over normative crossings. Closing up, the act of closing up is closing up corresponds to taking a hom from the monoidal identity to this complex. I should give a name to this complex. Let me call this bounded complex of this braid is beta, and let me call this complex the complex of beta. Okay? So if you take hom in this categorification from the monoidal identity to the complex of beta, then you get this thing associated to closing up. Okay? And so the theorem of sort of many people is that this hom space is the Khovanov-Rozansky homology. Yeah. Well, but I mean, like, there's all kinds of limited contexts when this is secretly Schur-Weil duality, where it happened first. Anyway. So this is one way of constructing Khovanov-Rozansky.
This is the foam stuff, right?
Yeah, so foams is another way of describing the Schur quotient. Although that's on the other side of duality. So foams is like a categorification of webs, and it lives over here. We're talking about over here. Of course, the Schur quotient here is the same as that, but it's a very different perspective.
If this is now not what Webster would do.
Yes, this has nothing to do with what, like, okay, this is the same thing as what Webster would do in type A. Again, as Webster proved, it's the same as lots of other things.
So with this one, the thing that Webster correctly would do is on the other side.
On the left-hand side.
Yeah, Webster would never leave the left-hand side, that's correct. That's correct. They do agree with each other. Okay. So now let's let n be 2n. Okay? And let's be sigma be this Dynkin diagram monomorphism, which swaps the kth wedge product with the 2n minus kth wedge product. Okay? So this swaps sort of one of these weight spaces k with 2n minus k. So by n, I mean n, and there's d of these, of course. So this weight space right here, with n, this is a GLD weight space. As an SLD weight space, it's 0.
I've got to totally lost. Which side are you on?
I'm trying to explain to you how you go through Schur-Weil duality. So please bear with me. There's an n and a d. I'm using them consistently. D is always on one side, n is always on the other. I sure did. It's a default tensor product of SLN representations. Okay? So this swaps k with 2n minus k. 2n is, of course, 2n. Okay? So this corresponds to some sort of involution tau acting on UQGLD with all these idempotents, right? That swaps 1k with 1 2n minus k. Okay? And if you look at what it does, like for example, if I had 4, 7, 5, 6, and 2n was equal to 8, I want you to think that like all these arrows are pointing up. It doesn't matter. I'm going to take 8 and subtract this, so I'm going to get 4, 1, 3, 2, and now this has to go the other way in order for this to work. Okay? So it swaps E with F. Okay? So there's this tau on this side, which swaps EI and FI. When you swap EI with FI, you think you should negate weight spaces because it sends H to minus H. Right? But we're in GL, and so we're allowed to negate weight spaces and add this sort of thing that does nothing. This is on the right side. This is on the left side. Yeah.
We'll change K to 2 minus K. Isn't this like a Dynkin involution of this last?
This is a Dynkin involution on this side. Yeah. That's skew duality. But on this side, it's the involution that swaps E and F. So this is like taking a transpose of a matrix whose fixed points would be SO. Okay? So on this side, it's not a Dynkin diagram automorphism. On this side, it is a Dynkin diagram automorphism. Okay. On the other side of skew duality, it's this sort of transpose, if you will, automorphism. Okay? And I'm talking about Schur-Wald duality right now. I haven't categorified it yet. Okay. So tau is an involution on UQGLN. It's basically defined like this. It fixes the weight space 1n, the 0 weight space for SL at D. Okay? And let me define, it also fixes the elements xi, which is my definition, which I'm defining as EI, FI, 1n, because it swaps EI and FI. So it sends this to FI, EI, 1n. But on the 0 weight space, E and F commute. Okay? And it also fixes what I'm going to call xi divided k, which is EI divided k, FI divided k, 1n. Now, that is not the divided power of xi. I will make this point very clear. So xi divided k is not x to the I to the k divided by k factorial. It's actually a much more interesting polynomial in the xi. That's a nice recursive formula that I can tell you. Should I give it to you? It's right here. Did I write it down? I didn't care enough. I did not care enough to write that down. Okay. So, what we observed, and what started this whole project and made it all possible, which is that the subalgebra of UQGLD generated by these xi's, which does include the xi divided powers, when you sprinkle in signs, you just put some minus signs in clever places, agrees with an algebra defined by Wenzel for the endomorphisms over SO2 n plus 1 of the spin representation. Okay, and I want to reiterate, these xi's are acting on the weight space n. That weight space corresponds to wedge n, tensor wedge n, tensor dot 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 dot, tensor wedge n, d times. And remember, wedge n is the thing that folds to the spin representation. Okay? So Wenzel had described the endomorphisms of the default power of the spin representation by generators and relations. He defined an algebra as surjecting onto this. And we observed that the algebra you get generated by the xi's is basically the same thing up to adding some plus or minus ones in there. It's the same mod 2. Okay? If you remember the beginning of this talk, we had the spin representation circle and the type A circle, and they were the same mod 2. If you just put some signs in there appropriately, they're the same. Okay? And so that gave us the idea that whatever you use, we're the same mod 2.
What do you mean by circle?
Just like, remember when I wrote down 4 choose 2, quantum 4 choose 2 versus quantum 2 q, quantum 2? Yeah, exactly.
You just mean that the one.
Yeah. The trace of tau versus the identity are the same mod 2. And so our idea was, okay, whatever categorifies this, which we know from quantum stuff, we should put some involution on it and take the trace of that involution and should categorify this instead.
You use like the I5, EI, not the EI, I5, and you say it doesn't matter.
Yeah, because N is the 0 weight space for SLD. So as far as the E's and F's go, they commute on the 0 weight space. EF minus FE equals 0, because it's the 0 weight space.
But on the letter diagram side, it looks like very different.
Yes.
Like,
But what I'm trying to say is, if you computed this on, like, say, NN, like 4, 4, okay, and I compute EIFI, which looks like this, that you can do some web relation, some web calculus, and see that these are the same. These are just equal to each other in the web calculus.
Are you trying to explain that there's some version of this Howe duality where you put SO on one side and some new thing on the other?
Yeah, you cannot do that. That's a completely different thing, and it doesn't work. It's not so easy. So there are all kinds of dualities people tried to do in type D, in type B, in type D, and so forth. But we're doing something very different than that.
Based on what you just said,
Yes.
why is it?
Okay, it is related, and okay, I will get there if I have time, which is looking less and less likely. But
Someone told you time here is not.
a time. Oh, okay. All right. So, if none of you want to go home tonight, no, just kidding. Yeah. Okay. I think if you wait, it will become clear. I have that part planned for the end of the talk. Okay. So what is our goal here? So the goal is to lift tau to an involution. Let me just say an automorphism of UQGLD, so this categorified quantum group, such that the objects EI and FI are swapped, and of course the monoidal these objects are swapped, the weights are swapped. But there's more here, because this is how it acts on objects, and this is how it acts on one morphism. We need to see how it acts on two morphisms. Okay? And a crucial fact is that the endomorphisms of 1n in the Schur quotient, are isomorphic to the homology of Gur n to n in the Schur quotient. Okay. So this should be in the case d equals 2. I am being an idiot. The endomorphisms of NN. Okay. Oh no, this is the categorification. This is curly. Yeah. That's all I can do. So it's not my fault. Okay. So the point is that these bubbles. So if you know KLR algebra, there are these bubbles with dots on them. Okay. These are like usually correspond to, you can talk about Schur polynomials. Basically, there's an action of symmetric polynomials, symmetric functions on endomorphism algebras. And so I want S lambda, the Schur polynomial lambda, to go to S lambda transpose. This is some description of an action on the endomorphism spaces. And if this is true, then I claim that in some endomorphism space, in some example, you see cohomology rings of Grassmannians appear. And this matches the involution on the homology ring of Grassmannians that I started the talk with. Okay? So we want that to match. Okay? That's going to give you what gives you the endomorphism. Remember that the Khovanov-Rozansky of the unknot, right? So that's the closure of a braid. That's supposed to be the Hom space in this category from the monoidal identity to the complex associated to, well, the identity, which is also the monoidal identity. Okay? And so, indeed, when this is labeled appropriately, and I believe this should just be labeled with N, so maybe I'm doing GL1 or something, then I get a Grassmannian. And this Grassmannian appears in many, many, many guises within bigger Hom spaces and bigger things, and we want this to be compatible. That's all I'm trying to say. So here's the part where I can't really explain too many of the details without ever talking about the Khovanov-Rozansky category, and I don't really want to, because it's a big technical piece of nonsense with lots of relations. But we did this. Yeah. Thank you.
And why should endomorphisms of one be the same?
So the inside, sorry, let me just say this. Inside the endomorphisms of N, there's actually a copy of, like, D commuting copies of this Grassmannian. Yes, sorry.
Why should that be true?
It's like our disk with one stop and one and you fold it to have a reflow language.
Did I get this right?
I mean, there should be some statement. The categorified should be something obvious.
It's already categorical.
Yeah, this thing right here is like N, and then I close it up. So the Khovanov-Rozansky homology of this is the default tensor product of the Khovanov-Rozansky of this. Yeah, I'm talking about the Khovanov-Rozansky 2 category for GLD.
Is that the same thing as that's called this scalar algebra, or what is the difference?
No, I did not ever mean to use the word KLR, because KLR is only describing positive half.
Okay.
You need to have both E's and F's in order to possibly define this.
It's the thing which involves both halves.
Yes.
Like the scalar algebra.
Yes. It's got cups and caps and bubbles and all that stuff. Okay. The theorem. Okay.
This is just some very sort of classical trace. That's the thing you drew up there.
This thing?
Yeah.
Yeah. Just.
Right.
Yeah.
But that is the homology that you have there. This is like Khovanov homology happening.
Yes.
So why are you relating?
Because they're the same. This is the other side of skew Howe duality way of describing Khovanov-Rozansky homology.
Something that's fancy on one side becomes very elegant. Can you tell us more about that statement?
Probably, although it's not truly my area of expertise. But yeah, I can try.
I mean, it must be something essential. So you're saying a fancy.
Like once you know, yeah, well, I claim that you can define Khovanov-Rozansky homology in the way that I said, that you have this Ricard complex associated to each crossing. You tensor them together to get a complex associated to a braid. You take the closure by taking Hom from the identity, and then that, I claim, agrees with the Khovanov-Rozansky homology. Having those two sides match requires doing some sort of singular circle bimodule matching or various kinds of ways that you can match these two sides up. But like for this talk, I'm going to use that as a definition of Khovanov-Rozansky homology. It may not be the definition you're used to.
Again, we are always on the right side.
Indeed.
I'm sorry. So that guy said it's Hom from one to the closure of the braid.
To the complex, just the complex. Taking closure is Hom from one dash. It's like Cauchy homology, right? Zeroth Cauchy homology is Hom from the monoidal identity. That's how you, yeah, it's a typical way to close things.
It's the same way you always do. Always,
No, I think I just had it
it's
somewhere.
always the same. It's always Hom from one to this. Always.
Okay. All right, so we wanted to lift Howe to an automorphism. We kind of had a template for what should happen, okay? And the relationship between the shared polynomials associated with lambda and lambda transpose had something to do with changing orientation. And remember, in Khovanov-Rozansky calculus, whether or not you know it, E is an up arrow and F is a down arrow. So we're changing some sort of orientation. You have no idea what I'm writing down unless you already know Khovanov-Rozansky calculus. Sorry, Khovanov-Rozansky calculus. But I claim that there's an automorphism. It sends the up arrow to the down arrow. It sends the up dot to minus the down dot. It sends a cap to plus or minus a cap with reversed orientation, and it sends a crossing to plus or minus the reversed crossing. And these signs depend on the ambient weights. And if you know this calculus, you know what I'm talking about. And if you don't, you'll just accept this, okay?
I realize my mom has it. But if I don't put Q, I just ask with involution on the EL. Is it transpose?
This is like the transpose, yes. This is.
Really the transpose, if I go down and up.
It sends EI to FI, that is the transpose. But it's an idempotented thing, so yeah. Okay? And the only problem with this is that this automorphism has order 4. It doesn't actually have order 2. We couldn't find one of order 2. It's quite surprising. But that's okay. Because we were also able to prove that, that when restricted to the subcategory, generated by capital Xi, which is EI FI 1n, it's an involution. Okay. So we have an involution on the part of GLD that actually acts on the part of stuff that we care about. Slightly surprising that there was no nice involution lifting transpose. But nobody had considered this kind of automorphism before. The Khovanov-Rozansky category has lots of automorphisms. But this was not one of the ones that had been previously considered. We have a theorem that describes the possible obstructions to this, and we were not able to prove that you can't. But we were able to prove that you couldn't and have it still be nice. This is a relatively nice dependence of these signs on weights. And we argued that if you could possibly lift it to an involution, then it would be a really gross dependence of the signs on weights. Okay. So let me now try to give a quick example. So this picture in the Khovanov-Rozansky calculus is what? I'm going to put an N on the right. The Khovanov-Rozansky calculus has some strands, and regions are labeled by weights. Up arrow is E, and down arrow is F. So this is a map from F, E, 1N to E, F, 1N. Down, up goes to up, down. Okay? And this thing is actually an isomorphism in the category. Okay? Now, tau of this happens to be this thing, still with an N on the right. And that's the inverse isomorphism. No, absolutely not. Okay. Did I decide that xi was going to be EI, FI, or FI, EI? I think I'm going to absolutely screw myself over if I don't switch back to FI, EI. Because I was not paying close enough attention to my notes. I was a little distracted, and I humbly apologize. That was very naughty of me. Okay, so down here is the object x. Okay, and up here is the object tau of x. Okay, And so I claim that this map right here is an isomorphism from x to tau of x. Now tau of this is a map from tau of x to tau squared of x, but tau squared is an involution, so that's just x again. Okay, and that's the inverse isomorphism. Great. So tau fixes xi. So if I like put eyes on these things, these would have to have different colors, but you don't know about that. It's okay. It fixes tensor products of these xi's, but not all summands of tensor products. So inside, say, xi plus 1 xi, you can do this computation, and inside here, as a direct summand, is, say, ei plus 1 fi ei fi plus 1. And this thing is not fixed by tau. You also have tau of it, which is fi plus 1 ei fi fi plus 1. It's ei plus 1, sorry. So here's like, I'm going to call this A, and this is tau of A. So this object is fixed by tau. So if I have a direct summand A, then tau of A also better be a direct summand. Okay? And this object just happens to not be isomorphic to this object. Okay? So there are plenty of summands of tensor products that are not fixed by tau, even though this is fixed by tau, up to isomorphism. Okay, so step 1 was constructing this lift of tau. But step 2 is doing something with it. I need to construct an action of tau on Khovanov-Rozansky homology, not just on this category. Okay? Tau is an automorphism of the category, but I needed to act on this Hom space, which is Khovanov-Rozansky homology. So how does tau act on Hom spaces? Yes. It's not as, please wait. Okay? So suppose that you're given an object, y, which is isomorphic to tau y. Okay? And so that you're given an object z, which is isomorphic to tau z. Okay? And I'm going to fix these isomorphisms, phi y and phi z. Okay? So now, given a morphism from x from y to z, I can get a square like so. And there's absolutely no requirement for this square to commute. Okay? There's no need for this to commute. Necessarily commute. For example, if it did commute, you'd then rescale this by 5 and it doesn't commute anymore. Okay? So suppose that we try to define tau star f to be another map from y to z. And it's going to be the map that you get by going this way around the square. So instead of going straight from y to z, you go down, over, and up. Okay? By the inverse map here. Okay? So then that way, tau would actually be acting by this star product on Hom from y to z, as opposed to sending y to z to Hom from tau y to tau z. Right? And I want it to act on one Hom space. Okay? The problem is that you're not guaranteed for this to be an involution. Okay? Like, doing this more generally, so this note, star depends on choice of phi y and phi z. Okay? Now, unfortunately, so if star holds, And then tau is an involution, and I'm about to define what tau is. And tau star is an involution. And star is the property that if I start at y, and I follow phi y to tau of y, and then I follow tau of phi y to tau squared of y, but that's just y, that this composition is the identity. Okay? The statement is that the inverse of phi is tau of phi. Yeah, I'm assuming that people don't know what equivariant means. So I'm defining equivariant. Tau is an automorphism of your category. It's a functor from the... Tau squared is the identity functor. That's what it means. That does not imply this at all. For example, you'll see. Please be patient. Okay? So note, if phi y satisfies this, so does minus phi y. Okay? Because I would put a sign here and a sign here, and the signs would cancel. Okay? So this phi is sort of like a nice way of identifying an object with tau of itself. And this was an example, right? I just said the tau of this is the inverse isomorphism. Okay? Whereas if I multiply this by 2, then the inverse isomorphism should have a 1/2. So that's not a nice way of identifying these things. Okay? So let me give some examples. So if this star holds for all the objects for phi y and for phi z, then this tau star operation is an isomorphism. Sorry, is an involution. Is an involution. Okay? So example 1, as noted above, would be FE1n and this sideways crossing. Example 2 would be FE1n and minus this sideways crossing. Example 3 would be A plus tau of A. So in order to have an isomorphism from y to tau of y, I need y and tau of y to be isomorphic. So I can't just choose A because tau of A was not isomorphic to A. A is this thing right there. Okay?
So this UQGRD, is a two-category?
Yep.
And the big XI, what are the objects?
Yep. They're objects.
The objects.
One morphisms. They're one morphisms. Sorry.
They're elements in the one morphism category?
Yeah, they are one morphisms. So one n underline is an object, and X is an endomorphism of that object, which is a one morphism. And of course, there's endomorphisms of Xi, which are two morphisms.
What did it mean to say tau fixes Xi?
Up to isomorphism. Tau of Xi is isomorphic to Xi.
Not with a fixed isomorphism, or
I can't do it. Thank you. That was loose.
So even though EF is the same, EF and FE are isomorphic.
Yes, but they're not the same object. And that choice of that isomorphism is interesting data.
just want to know at this point. So if you're saying when they say tau fixes Xi up to isomorphism, you mean there's an isomorphism which you do not at this point specify. And if you had specified it, then I would have to write that.
And if I had specified it, then you would have to write to ask whether star holds for that isomorphism. That's right. Great. So once you have fixed your isomorphism from an object to tau of it, then you can define this star map on Hom spaces. Okay? There's a general formalization for this kind of category. So here's a definition. Let tau act on a category C such that tau squared is the identity functor of C on the nose. no isomorphism of functors. It's just the identity functor. Okay? The equivariant category C sub tau is the category whose objects are pairs of an object in C and an isomorphism from y to tau I such that star holds. Okay? So these are examples of objects in the equivariant category. And a morphism would be a map that makes the natural diagram commute. All right, so a map y to z such that y to z to tau I to tau z commutes. Okay. So various objects in the equivariant category include all of these objects and their tensor products. And given y phi y and z phi z in the equivariant category, then you get a star action on the Hom space in the original category from y to z. Okay? So if you have any morphism where this square doesn't commute, then tau star would measure how it doesn't commute. Okay? And the statement is that the +1 eigenspace of this action is exactly Hom from y phi y to z phi z in this equivariant category, because if it's a 1 eigenspace, that means tau doesn't change it, and so the square does commute. Okay? And the -1 eigenspace is actually Hom in this equivariant category from y phi y to z minus phi z. Or I could put the minus sign over here instead. Okay. So you should think that this eigenspace, this Hom space, the original Hom space, gets split in half into two pieces, the +1 eigenspace and the -1 eigenspace, which represent two different Hom spaces in the equivariant category. Questions about that? Equivariant categories don't get enough space in the literature. They're very natural things. But like, because Lustig didn't define it this way, nobody else does. Okay. So let me now define like bold X I to be Fi EI 1n together with this morphism that I wrote down before. Okay. Now, I'm just going to explain to you how you do a calculation in the equivariant category. Because it's not an easy thing to compute in the equivariant category. So what? Yeah, this xi is an object in the equivariant category. Is the structure? Yes, exactly. That's right. So here's an example. So in the original equivariant category, the original categorification, not equivariant, we have, if you tensor xi with xi plus 1, let me call this xj. J is going to be I plus 1. If you tensor xi, xj, xi, and you decompose it into summands, you get xi divided 2 xj plus xj xi divided 2 plus quantum 2 copies of xi divided 2 plus 1 copy of xi plus a plus tau of a plus b plus tau of b for some other b that I'm not going to bother to write down. It's got a lot of summands. It's a big thing. Okay? So now what about in the equivariant category, what if I tensor these bold xi's? Okay. So let me tell you how you would compute how that decomposes in the equivariant category. Okay. Say what? Well, you can do tensor. You just this is as an object xi, xj, xi with the tensor product of the structures. So. Okay. So this is the isomorphism from this thing to tau of it. So how do we compute how this decomposes in the equivariant category? Let me explain. Here is an object that might be a summand. Okay? If it's a direct summand, that means there's a projection map and an inclusion map. Okay? Such that the composition is the identity. Okay? Let me write them down. I mean, you don't have to understand anything about calculus. You can just accept that I'm writing it down. So let's see, this is down, up, down, down, up, down, up. This is a map from down up, which is xi, down up in a different color, that's xj, down up, that's xi, to divided 2 xi, and then xj. Okay, that's a particular morphism in the category. Okay. So let's compute tau star of p. So I is going to be the same thing upside down. And I claim that you can compute that I composed with p is the identity of this thing. Okay, that's a computation in this calculus. Okay. Okay. Now, tau star p. Sorry, what is tau star p supposed to be? Okay. Well, I have p. Sorry, I'm about. Let me not draw the arrows for a sec. Yeah, so this is tau star p. So the first thing I do is I take tau of p, which is p but with the arrows reversed, okay? So I put some arrow reversals. And before it was down up, so now it's up down. Now this is a map from tau of the bottom to tau of the top, compared to what it was originally. Then I pre-compose and post-compose with the isomorphisms. So that's one of the isomorphisms. And then on top, there's another one of these things. So this is sort of applying phi of xi, xj, xi, and this is phi inverse of xi squared xj. Okay. And now if you look at the orientations on bottom and top again, down up, down up, down up, this is xi, xj, xi again. And this is xi squared xj. Okay? So this thing, tau star p, lives in the same Hom space as this. Okay? And then you can compute tau star p composed with I. And I get minus the identity of xi squared xj. Okay? It's just a computation. You can trust me that it's done. What does this tell you? Okay? So what this tells you is that tau star p is equivalent to minus p modulo the kernel of composing with I. And this Hom space modulo the kernel of composing with I is something called the multiplicity space. It tells you how many times this thing is a summand of that one. It's a summand with multiplicity 1, and this quotient is a one-dimensional Hom space. Okay? And this is telling you that tau is acting on that one-dimensional Hom space by multiplication by minus 1. Okay? So tau acts by minus 1 on the multiplicity space for this thing as a summand of that thing. Okay? Multiplicity spaces is a thing you can define as a quotient of Hom spaces, and they're very useful things. Okay? So I claim that the conclusion of this is that in the equivariant category, this equivariant category, then what's inside xi, xj, xi, what's a summand is xi to xj, but with the minus sign. Sorry, let me xi squared xj, but with minus the usual isomorphism. Okay? So this might be the object that I might call, in quotes, minus xi to xj, end quotes. Okay? So this is the kind of computation you have to do to work in the equivariant category. This, like the fact that this is the kind of computation you have to do wasn't in the literature, which is kind of annoying, so we had to fill that in. But,
So, like, you reach the competition by saying how
yes, that's right. So you used to have an old decomposition that you computed painstakingly in the original category. Now you have to compute how tau acts on each multiplicity space. That's the extra work you have to do.
So what was not in the literature, how to use diagrams, or?
What was not in the literature is how to compute the action of tau on multiplicity spaces.
So in other words, how to inform them.
Yes, that's right. Was the statement that this calculation was sufficient. This is abstract nonsense. It's nice to have this abstract nonsense in the literature.
The fact that you do this calculation, you know question how to do it.
Yeah, maybe I'll say that. Okay, so in the end, you compute. And so now, just to avoid writing things down again, I could tensor all these together, and I get minus sign here, minus sign here, minus 1 to the n here, plus sign here. And these things, like there's really only one way to do it up to isomorphism. And so there's the decomposition of the equivariant category. Cool. So you have an equivariant category. What's its Grothendieck group? The equivariant Grothendieck group is not the Grothendieck group of this category. Okay? It is the quotient of C tau, sort of the usual Grothendieck group, the split Grothendieck group, by the relation that the symbol of y minus phi is minus the symbol of y phi. Okay? And this is the version of a Grothendieck group where sort of traces of tau on Helm spaces actually gives you something about the Grothendieck group. Okay? But let me make a point. So like, suppose you have an equivariant category. How big is its actual Grothendieck group? Okay? For every fixed point in the original category, for every isomorphism class of indecomposable object that's fixed up to isomorphism, like this FE1N, there's actually two distinct indecomposables in the equivariant category. The +1 version and the -1 version. Okay? For every object that wasn't fixed, so for every indecomposable like A that's not fixed by tau, then for every orbit, for every free orbit, you actually have one object. Okay? If I take this 0, 1, -1, 0, and I put a minus sign on it, it's just isomorphic to the original. Like 0, 1, 1, 0, and 0, -1, -1, 0 are conjugate matrices. Okay? So there's like every orbit of size 1 under tau becomes two objects, and every orbit of size 2 under tau becomes one object. It's a very strange thing, this Grothendieck group. Okay? But then we take this relation on the Grothendieck group. Okay? What happens in this relation on the Grothendieck group? Well, you've got those two objects up there, and now in the Grothendieck group, they're just opposite to each other. They cancel each other out. Okay? But as far as Helm spaces are concerned, it gives you, as far as the overall size of the Grothendieck group is concerned, those sort of only contribute a one-dimensional space. And then this object is actually isomorphic to its opposite, which means that it's 0 in the Grothendieck group. Yeah? So all of these orbits disappear. So the equivariant Grothendieck group has the same size as the number of fixed point objects in the original. Okay? but it's not the Grothendieck group of anything.
Sorry, is this the usual thing? Is this
It's hard to find this written down in the literature. So I wrote it down in my, I'm like not claiming to have invented it. It's definitely not me, but people didn't write things down carefully. So in a paper called Folding Uncircled Bimodules, I wrote this down carefully. Yes, you're correct. It's yes. Oh, okay.
Passing to this equivariant part would be like passing some stack function or something.
Yeah, so what often is different about equivariant geometry is that usually you don't have a strict action. I've said that tau squared is equal to the identity functor. Yeah, but like when in algebraic geometry, you're usually keeping track of a lot more data in your. Yeah, you're right. You're right. Yeah. So the equivariance data is more complicated, but yes, that's fine. So what you should do is you should take an element of the dual group. If you have a group acting, then the Pontryagin dual acts on the equivariant category. And then choosing an element of the Pontryagin double dual, you can weight the Grothendieck group by a character. And that's what's happening here. And this is explained in my Folding Uncircled Bimodules paper. But I don't talk about the general case of like groups of topology. I just talk about finite groups. All of these statements are more complicated in the non-semi-simple setting. Whew. Lots of questions. I'm glad this goes on forever. Okay. So this equivariant Grothendieck group, I might denote C adjoint tau minus 1. Because you're twisting by minus 1 as an element of the Pontryagin double dual, but don't worry about it. Okay. So the claim is that, in C,
This is not a thing you could have done if someone just handed you equivariant growth. You have to still remember something about the tau action to do this.
yes. Yes, that's right. So in C, if an object M is like the sum over indecomposables B of the dimension of the multiplicity space of B and M times B, that's like how things normally decompose in your usual additive category. In C tau, instead, you'd have M phi M is equal to the sum over those indecomposables such that B is isomorphic to tau of B, and none of the other indecomposables matter, of the trace of tau star on the multiplicity of B and M times B phi B. And you've just chosen one of those for this purpose. Choice of here gives you the choice of that. So this is the sense in which traces suddenly play a role. But it's because they describe Hom spaces, as I sort of said somewhere here. And so sort of the statement of folded skew Howe duality, so this is your theorem conjecture, is that we had this UQ GLD with some weight spaces, and I'll put n's on both sides. So this would map to the endomorphism algebra of the nth wedge product to the dth power. Now, I'm just reminding you of the original statement. This is non-categorical. Okay. The categorical statement inside this, inside the categorification, I have the subcategory generated by the xi's. Okay. This lives inside 1n. Okay. And let's see. Okay. What's the best way to say this? Okay. So, actually no. First, let me talk about Grothendieck groups. This is the best way to say it. So inside here, I've got the subalgebra generated by the little xi's. Okay. And these do, in fact, surject onto this. Okay? And in fact, they pass through this quotient, which is the Schur quotient. Less than equal to 2n GLD, which is isomorphic to its image. That's right. And the claim is that this thing generates the Schur quotient. Yeah. Okay. And now, when we categorify, the statement is that if I look at the xi's, the thing generated by the xi's, and instead I take the minus 1 Grothendieck group, that this is going to map onto the thing generated by the xi's and minus 1 Grothendieck group in the Schur quotient, the categorical Schur quotient. And the conjecture is that this is isomorphism to the endomorphisms of S tensor D, the spin representation. This is a decategorified statement in some sense. This is a Grothendieck group statement. Okay.
The existence of the maps is not a conjecture, it's just
This part right here is the conjecture. Yes, there's a map. Like, the only question is to argue that this is not bigger than you think it is.
Can you remind me what's the S? What's the S related to?
S is the spin representation. So S, so if you were doing type B, 2, say.
How is that? Not the N related. So why N C to N? How is that related to S?
How is what related to that? Sorry.
The wedge N C to N.
Yeah, so under this folding of Dynkin diagrams, okay, wedge N is here and S is here.
And the vector space, how?
They're not. Again, like vectors, yeah, the vector spaces aren't related. Maybe I should say there's one big vector space that quotients to both of them. It's like a big vector space with an action and involution, and if you set that involution to 1, you get this thing, and if you set that involution to -1, you get that other thing.
There is an invariant part.
You're asking, yeah, there is an invariant part here that gives you this, perhaps. That might be on the nose, yeah, on this side of scroll to duality. You're right. Sorry, you're absolutely right. I'm wrong. Yes, that's correct. Yeah, this is that old Clifford business. Yes, you're right. Thank you. Yeah, you're right. Okay. And so then the additional theorem is that these complexes, these sort of Ricard complexes associated to braids, do admit invariant equivariant lifts. So they are nicely isomorphic to tau of themselves. And so because of that, there isn't a tau star action on Hom from the monoid identity of N to the complex of a braid, which is Khovanov-Rozansky homology. And then we checked that you have to check some Reidemeister invariants and Markov invariants to say that this is a link invariant. And we checked that those invariances are compatible with the tau action. So it's compatible with Markov and Reidemeister. And that implies that the plus or minus 1 eigenspaces are link invariants. And so if this theorem were true, if this conjecture were true, then they would be the link invariants associated to the Reichardt-Ticken and
So which part is the conjecture part?
just the fact that this Grothendieck group is isomorphic to that. This could be much bigger. Like, we don't really have a classification of the indecomposable objects. So who knows what these indecomposable objects are? There could be a bunch of crazy ones in here. Nobody knows anything about the growth. Like,
nature of the problem is you have no tool.
Say that again?
The nature of the problem is you have no tool to compute.
Yeah, right. We have tools to compute a part of this Grothendieck group, but like the actual indecomposables, we can't drill down. Yes, exactly. We have no tools to compute. But, you know, we can compute some relations between the objects we know by doing those kind of calculations up here. We can't compute the relations between the objects we don't know. Yeah. And nobody knows the canonical basis of the quantum group, you know?
So, sorry, you'd like to relate it to grading range itself.
Yeah, so yeah, that's easy to do. So if you remember, there's like, I wrote down this complex for this. Okay, and in our sense, that's just literally like x, x2, x3. Like this x basis was almost chosen for this to be nice and positive in that basis. So this description actually of the braiding in type B is actually a new description. Like it's a nice positive description.
The morphisms could be bigger than those generated by grading, or
This could be much bigger than that. We have a map. We just don't know it's an isomorphism. We know it's surjective.
It's kind of a common problem.
Say it again?
It's kind of a common problem.
Yeah, it is a very common problem in the subject. And the other thing I want to point out is that, like, what is the kernel of this map? Right? It's pretty easy to describe in type A. Nobody knew the description in type B before, and now we have a conjectural description of it, which we're proving in an upcoming paper. That the kernel of this map is exactly the symbol of x divided to the n plus 1. Which is nice. That's kind of how it's similar to things that happen in other quantum groups. Usually the kernel is generated by some indecomposable objects that go to 0. That's what you'd want to be true. It's generated by some canonical basis elements in the Grothendieck group, which are the symbols of indecomposables. So this is sort of a new statement, like the second invariant there. I don't have to give the rest of my talk if you don't want me to. I'm happy to. This is roughly where I was going to stop and continue if I had time, right? So what? The rest of the talk was to match this with things in the literature a little bit, to explain a little bit more about this algebra and S tensor D. Because this is related to something called an I quantum group. And this is the first example, I think, of an algebra like that's been categorified in two different ways, with two distinct kind of canonical bases. Okay, great. I'm running out of chalk that isn't a nub. I think I'll use the yellow, unless I should. So I'll point out that this part of the talk, like the true expert on anything decategorified, and the literature on I quantum groups and stuff is Elijah Bodish. He is a wizard who has read all this stuff and knows it very well. Say what? Elijah Bodish, my collaborator on this work. Former PhD student. So, let me just, part of what we do in this work, so we do start it in the paper that I cited, and we're finishing it in work that should go on the arXiv in a month or two, is we use this to produce a description of type B webs. Type B webs are previously unknown. Type A webs I gave you some pictures of before, but type B webs were not known, okay? And so a web is some sort of diagrammatic description of morphisms between tensor products of fundamental representations of a Lie algebra, or its quantum. Some sort of diagrammatics. And so just to be like, so inside S tensor M, sorry, the endomorphism algebra of S tensor M, we're going to define a picture that looks like this. Okay, so I want you to think that all of these strands are like labeled with S. Okay, so So this is a map from, I should probably do S tensor D. This is a map from S tensor D to S tensor D, the same labels on bottom and top. And this is going to be defined as the image of the Grothendieck group symbol of X. This is said to be ith strand. And then this is divided K. Okay?
Sorry, what does K stand for?
K is the divided index. That's all it is. So this is like EIFI. I want you to think that what we do is in GL webs, here's what I want you to think. In GL webs, we have N, 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 N. Okay? And then we have E to the K, F to the K, which looks like this. Okay? And then we have this operation, tau, which sort of swaps this. Tau of this looks the same, except the rungs are swapped. But it turns out those are equal. Okay? And I want you to think that when you like take the tau version, this kind of squashes into like a K-labeled thing. Okay? Okay. So this is some endomorphism of S tensor N. Really, if you want it, you could focus on just S tensor S. Okay, endomorphisms of S tensor S. Okay? And if you look at S tensor S, and you decompose it into its summands, then actually every single other fundamental representation is a summand. Okay? So this is the irreducible representation associated to the Lth fundamental weight. Okay? For L between 0 and n minus 1. Okay, so I guess when L is 0, it's the trivial rep. Okay, but all the other fundamental representations are exterior products. There's a Q deformation of this, so forgive me, I'm just telling you what happens at Q equals 1. Maybe I should put this in quotes. But all these other fundamental representations are summands of this. Okay, and so that with multiplicity 1. And so that means that there's some sort of map from S tensor S to L, which is the projection map, and some map from L to S tensor S, and these maps are defined uniquely up to scalar. Okay? And when L is 0, you have sort of cups and caps, coming from the trivial representation. So all of these maps exist. These sort of describe, I can like pick an element of this one-dimensional Helm space and draw it like this. Okay, and I've picked a particular element in my one-dimensional Helm space. And so we've picked the particular elements, and we've done a lot of computations, and we can compute, for example, that if you take the rotation,
So to speak, everyone with before drawing these four being put down there, X1 is 10 q.
That's right. That's right. And one thing we computed is that this rotates to n minus k. And so that's pretty cool, because this might has a chance of giving you like a rotation invariant basis of this endomorphism space.
Do you need to put the pointed bracket and the -1 subscript to see which of that?
Yeah, and like the, and in the equivariant growth. And we, so here's another computation you can do. Like X itself can be described as this. So this is the identity of S tensor S, and this is the rotation of like merging two S's to a 1, and then splitting a 1 into two S's. So there's some cups and caps, and this thing that built this thing.
So should those strands carry like a direction, or?
No, there's no direction. S is self-dual. S is coherently self-dual. It gives you signed positivity. It's the dimension of a positive +1 eigenspace minus the dimension of a -1 eigenspace. It's the difference between two positive numbers. I know, love it, right? Plus. Okay. So we have polynomials in some sense in the H's that describe the X's. And sort of we found a whole bunch of relations explaining between these different things.
So what's the horizontal bar?
The horizontal bar is let me describe it like this.
When you have these related graphs, I mean, if these x's are always expressed in other ones, what is one of the x's to begin with?
The point is that it's a canonical basis, right? I'm getting there, I'm getting there, I'm getting there. Just to give you examples of the kind of relations that we do. So in the literature, I'm going to let bi be xi minus 1 over quantum 2. Plus 1 over quantum 2, which is what you're thinking of here as this h thing. Okay? And Yorgov, Klimek, oh God, did I get the I and the Y? Yorgov, Klimek defined an algebra, which they called U prime Q S O M. Okay? They defined it by generators and relations as being defined by some BIs modulo some relations. These relations are kind of like the Serre relations in some sense. Okay? And why did they define this thing? They define this thing as, well, there's two different purposes for this. Okay? So they were defining it as being a description of the I quantum group associated to SOM inside SLN. So what is an I quantum group? Whew. You've got a Lie algebra, you've got a Dynkin diagram, you have a automorphism, say, of that Dynkin diagram, maybe. So inside the Lie algebra, you could take fixed points and get that thing. In this case, you take transpose, you take fixed points under transpose. The quantum group is not so nice. You can't just do this in the level of the quantum group. Okay? So for example, like inside the quantum group, would you take E plus F? That's like mixing up weight spaces in a nasty way. Like what's fixed? So so there is something that you can define inside the quantum group. So this thing is a subalgebra of UQ of SLN. And it's a subalgebra, but you want these things to be Hopf algebras because you want them to act on tensor products. And it's not a sub-Hopf algebra. It's not closed under the coproduct, but it's what's called a Hopf ideal. Okay? It's the next best thing. Okay? So this is called a Hopf ideal subalgebra. You look like you were poised to say something, you know. Okay. The sort of given any representation of SLN, you can define the corresponding representation of UQ SOM. There's a reason to care about these Hopf ideal subalgebras because, like, you know, when you do Schur-Weil duality in type A, everything is so easy. On one side you got the Wall group, and on the other side you got the quantum group. Or you got on one side you got the Heck algebra, and on the other side you got the quantum group. In any other type, it doesn't match up so easily. Right? So if you put the quantum group on one side, then you get some sort of Brouwer algebra on the other side. Or if you put the Wall group on some other side, you get some kind of Hopf ideal coalgebra on the other side. And life is complicated. So this is one of many reasons to be considering these Hopf ideal subalgebras. Yes, and it's also a thing that appears. So one of the things that's nice about this, maybe I'll put it this way, like SLM is inside SLM plus 1 is inside SLM plus 2, in a way compatible with an inclusion of Dynkin diagrams. Right, so forth. But it's not true. So SOM, you know, is inside SOM. You know, you want to do some sort of similar thing here, right? And this may be the case for Lie algebras, but it's not the case for quantum groups, okay? And the way that you know this is not a thing that you can do for quantum groups is that the Dynkin diagram of this is type, like one of them is type B and the other one's type D, and these Dynkin diagrams don't even include into each other, okay? So like this process is not gonna work after you quantize it, but there is going to be a chain of things like this inside this chain.
Would that have worked if you skipped the odd ones?
I don't think so either. Anyway, so there's a bunch of reasons to study I-quantum groups, and I-quantum groups, unlike normal quantum groups, do not have a triangular decomposition. You should think of the elements in here as being like E plus F. So there's no positive half and no negative half. Okay? So you can't do usual highest weight theory. But you can do usual induction theory. So the way that people study representation theory through chains of algebras and like standard Young tableau and stuff like that does actually work for this particular family of I-quantum groups. So, what Yorgov and Klimek did is they classified the representations of this I-quantum group. And what I'm going to do right now is just straight up put a minus q squared here. Because when you're matching them with us, you have to put a minus q squared as the parameter. Okay, so let me just put a minus q squared there.
You categorify the standard one.
Say that again?
Categorify the standard into
Yeah, surely a good Webster style. Yeah, in Webster style. Okay. So, what are the kinds of representations there are of this algebra? Well, certainly you've got this thing inside SLM. So you could restrict modules and get a bunch of representations this way. And they computed that when you do, that these BI act diagonalizably with eigenvalues plus or minus quantum k. Okay? And in particular, if you have plus quantum 5 as an eigenvalue, you also have minus quantum 5. Like the Weil group acts on these things with a minus sign in some sense. Okay? And so things for which you have these eigenvalues, they called classical representations. Well, even if you think about SOM inside SLN, it's supposed to be the same M, sorry. Even if you think about SOM inside SLM, you don't get all the representations, even at q equals 1 from restriction. You only get the even representations. There's also the representations of spin rather than SO, so there's actually yet more classical representations. But there's also more classical representations, lifting the sort of half integer representations. And the eigenvalues are, again, something that you can write down, and man, I don't really want to do it. It's like 2L plus 1 at QI divided by quantum 2 at QI, whatever. It's some collection of eigenvalues that you can write down. Okay. But then when there's some other collection of representations where the eigenvalues are plus or minus half integers at Q. And where do these come from? Well, so Wenzel realized that there was a map from U prime minus Q squared SLM to the endomorphisms of S tensor M. I think I have the correct M here, as a module over SO n plus 1 Q. Okay. He defined where these BIs went. And he argued that this was surjective, okay? Although he couldn't identify the kernel. Okay? And that BI have eigenvalues like this. So this is a source of some representations. In these ones, however, if you have plus this as an eigenvalue, you don't have minus that as an eigenvalue. Okay? So you get some signs this way. So the eigenvalues of bi happen to be -1 to the j minus 1 to j minus 1 over 2. So the signs are linked to the quantum number in this example. I might call these type 1 non-classical. This algebra also has an endomorphism which just puts a random sign on any random bi. You can just send bi to b3 to minus b3 and fix all the rest of them. And that's an endomorphism of this algebra. And so by twisting under such isomorphisms, you can put arbitrary signs on these things, however you want. And that's how you get the rest of the non-classical representations. And the theorem is that all representations are either classical of one of these kinds or non-classical of this kind. Okay. So that was what, between Wenzel and Iorgov-Klimik, what they did. And then, so, cool. Okay, so people have categorified representations of SLN. Okay. When you categorify something, you equip it with a nice basis called a canonical basis with nice positivity properties.
Is the word canonical basis a thing with a definition?
No. Canonical basis is the image of the indecomposables in the Grothendieck group. That is the definition, if you will. And so, following that perspective, Wei-Ching Wang and many collaborators, Brendan, about like I can't list them all, started this program to categorify I-quantum groups, and in particular to categorify and that started with actually looking at the Grothendieck group and defining a canonical basis. Okay, and what properties canonical bases should have is that ideals spanned by subsets of canonical bases are a nice thing. So like the quotient of the action of this thing on a given module should be a quotient by an ideal, and that ideal should be spanned by canonical basis elements. Like canonical basis elements that either go to 0 or they don't go to 0 and they go to a basis. And so what they did is they computed canonical bases adapted to these classical representations, the ones restricted from SLM. Okay, and of course, they were viewing this as associated to this pair SOM inside SLM as a fixed points under transpose. That was their motivation. But these canonical bases are not adapted to all of these non-classical representations at all. Okay? And so what we do with signed categorification is we claim that this signed Grothendiecker, so this is the conjecture, right? That this thing is the signed Grothendieck group of this sort of equivariant category inside the short quotient. And that the indecomposable, the self-dual indecomposables here descend to a basis of this, which we call like the signed canonical basis. And that it's compatible with these non-classical representations. And so it's like two different bases for the same algebra compatible with two different families of representations. It's kind of wild, and this has never happened before. But basically, there's a large literature on categorifying I-quantum groups, but that entire literature is adapted to a different family of representations than our weird equivariant categorification is adapted to. You definitely get a different basis.
I am not following. I thought your quantum group is standard one, and this is some other.
This is some weird I-quantum group. That's it.
Yet you are able to say something about it. That's surprising.
Well, the surprise is that it appears in both a standard way and a non-standard way. And our approach gives you the non-standard way, whereas the approaches that have been followed by the standard I-quantum group literature is doing the standard way.
Why should you be able to say anything about this other quantum group? That's not the. Okay.
Which will show well type A on one side, type A on the other side. Now, what happens if you try to go to a different type on one side is not that you get to go to a different type in the same way on the other side. That's not how Sherlock works. Instead, something screwy happens on the other side. When you go on this category,
against this.
And this he's explaining as a very important people have told you something about it, in particular categorification. And that categorification precedes it. It means that this Grothendieck group part has a kind of basis coming from the representation of acts, whatever. And
I didn't care about how it all is first. I wanted to know how to categorize my B looking variance, and now I'm completely lost. And I didn't care about the left hand side or the right hand side. I just want to know whether we have categorified standard Q, G, or G type B.
Yeah, so what we categorify is that statement for the spin representation. But the notion of what it means to categorify is new, right? We categorify it in the equivariant sense. So we don't give for this 4-dimensional thing, we do not give a 4-dimensional vector space. We give a 6-dimensional vector space in involution. And for other things that aren't the spin representation, we haven't figured out how to do it yet, but it should be describable by the equivariant category of a 2-category. Unfortunately, where tau doesn't fix the objects anymore, and it's more complicated. The role of this other quantum group is that it surjects onto these endomorphism spaces. So in theory, link invariance can be computed here, on this side. The link invariance could be computed here. Yeah, that's right. The link invariance could be computed in this wacky algebra. And this wacky algebra was already studied. As well as in, yeah, that's right.
As well as in the ordinary one.
Yes.
which side is which side?
Yeah, I think they got flipped to the way that I drew the picture originally. So,
So the equivariance that we asked about discussing, these are the ones which Webster would have also called the same thing, or
this is a new, completely unrelated to Webster construction. That's right.
Except for one thing. The one thing that's different is that like in our world, you'll get, like if you categorify actual representations, you will get a representation of size.
We do something different.
Yeah, that's,
yeah,
exactly.
This where you get something bigger.
Yes, we get something bigger. That's right.
Right.
Exactly. And there's like 2 different sides of this world, right? Like there's 2 different ways to study representation theory. So it's not sort of so surprising there might be more than one way to crack this egg. Or to kill this stone with a bird. I don't remember. Eat this Reese's. Yes.
So the first theorem you assert is that the transpose on matrices lifts to a now more 4 action on categorified UQ. That's statement 1.
Statement 1.
That's statement 2. You assert that the grade group action on the map, the grade group to UQGLN.
Yep.
This map is like bias times verbal nonsense, whatever.
Yep.
And that map factors through or lifts to
The equivariant.
fixed points of that action.
If that's what you want to call the equivariant category, then yes. Exactly. Correct.
And then, so that's kind of like the main theorem, and then that's how you compute all of that.
That's right.
And then some conjectures on how it tracks.
Correct.
And that's what I heard.
Yes.
So in this unknown example, right, we said that the +1 eigenspace is must categorify is not invariant, and -1 eigenspace is also not invariant.
Yes.
But presumably, it could happen that you can't really diagonalize and you get this like 0, 1, 1, 0 as you had here.
Right.
I mean, do you expect that to be a non-invariant too?
I mean, so like the original type A invariant is this whole 6-dimensional thing.
But,
That's right.
You know,
And I'm saying that actually inside the 6-dimensional one canonically splits as like a 5-1 when you keep track of that.
Some crazy knot. Are you sure that this kind of phenomenon will happen again, or?
Yeah, that's what we proved.
You proved.
Yes.
There will not be a 0, 1, 1, 0.
No, there is. But
There is.
how he uses it.
Yeah, I mean, this is a 0, 1, 1, 0 situation.
No, I mean that you can.
But maybe what's really important actually is that the +1 eigenspace and the -1 eigenspace, in some sense of all these things. Okay, I don't want to mix up. No, that's in the Grothendieck. Yeah, this is in the Grothendieck group. No, this is an invariant. This is not in the Grothendieck group. Sorry, I was about to say the +1 and eigenspace correspond to something canonical, but that's a lie. That's a lie.
Let me ask this question differently. Okay. Can you make an invariant where instead of taking this +1 eigenspace minus 1 eigenspace, you just throw away everyone with the 0, 1, 1, 0?
I do not know how to do that.
That's more like the thing we do.
That's what we do there. That will give you a 4-dimensional space.
Yeah. Now there might be a way to do that.
Why don't you do that? I mean, like,
Yeah.
Category, you can see.
Right. So things of the form 0, 1, 1, 0 are exactly the induced modules, right? Like these form a monoidal ideal. So we could take a quotient by these, and that would be canonically defined.
And that would be some invariant. You take your guy.
Yeah. And that's basically what you're doing when you're taking the twisted equivariant Grothendieck group, right? Like,
So that's yet another invariant.
yes, that's right. Yes, that's right.
And then you would have some 4-dimensional.
That's right. And in fact, since these things are probably both injective and projective, you might be able to canonically find a complement rather than taking a quotient. So you might be able to do that.
So we see that we will be able to prove that if you take vector scalar algebra, it will be completely separate.
Yeah. So you're wondering whether Webster's will actually just give you this in some canonical way. I would have no idea how to prove it, but that would be cool. That would be great. Thank you.